Every single day, every time you send an email, buy something online, or log into an account, there's this invisible shield at work, protecting your information as it zips all over the globe. Today, we're going to pull back the curtain on that silent guardian, the world of cryptography.
It's a question we should all probably ask more often, right? How are your secrets kept safe online? Every time you see that little padlock icon in your browser, you're looking at the result of a symphony of mathematical processes. And they're all designed to do just one thing: keep your private information private. So how does it all actually work?
Well, at its very core, cryptography is the science of secret writing. It's all about creating systems that let two people talk to each other securely, even if someone else, what we call an adversary, is listening in. It's kind of like a digital cat and mouse game that underpins almost everything we do on the internet. So, to really get this, we first need to understand what we're trying to achieve. And believe me, it's not just about hiding things. Modern cryptography gives us a whole framework for trust, and it's built on a few really key goals. Think of these as the 4 pillars of secure communication. First up, you've got confidentiality, which is just keeping your data secret. Then there is integrity, making sure the message you got is the message that was actually sent, with no changes. Third, we have authentication, which is all about proving who you're talking to. And finally, non-repudiation, which is a fancy way of saying you can prove someone sent a message, and they can't deny it later. So, let's look at the tools that make all this happen.
The first tool, and definitely the most famous one in the whole cryptographic toolbox, is encryption. This is how we get confidentiality. We're basically just scrambling our messages so that only the right person can unscramble them. You can think of it like putting your data inside a digital safe.
Now, encryption isn't a one-size-fits-all kind of deal. It really comes in 2 main flavors. You've got symmetric encryption, which is like a sprinter. It's super fast, uses shorter keys, and it's perfect for encrypting huge amounts of data, like all the traffic in a VPN. And then you have asymmetric encryption. Think of this one as more of a marathon runner. It's slower, it uses much longer keys, but it's designed to solve one very specific, very important problem.
Symmetric encryption is beautiful in its simplicity. You have one key. That's it. You use that key to lock the message, and your friend uses the exact same key to unlock it. It's incredibly fast and efficient. But you probably see the problem here, right? You and your friend have to somehow share that secret key before you can start talking securely. How in the world do you pass that secret key without someone grabbing it first?
And the answer to that problem is asymmetric encryption. This is so clever. It uses 2 keys that are mathematically linked: a public key, which you can give to anyone, and a private key, which you guard with your life. So anyone can use your public key to lock a message and send it to you. But, and this is the magic part, only you, with your matching private key, can unlock it. This just elegantly solves that whole key sharing problem.
Okay, so this brings us to one of the most brilliant ideas in all of computer science. Since symmetric encryption is fast for the main conversation, but asymmetric is great for getting started, modern systems just use both. They use the slower but super secure asymmetric method just to agree on a temporary secret key. And then, for the rest of the conversation, they switch over to the fast symmetric encryption using that new key. But how do they agree on that first key without anyone seeing it?
This is where the Diffie-Hellman key exchange comes in, and this paint mixing analogy is just perfect. Imagine Alice and Bob want to create a secret color they both share, but they can only send paint cans over a public channel where anyone can see. Okay, so first, they both agree on a common color, out in the open, let's say yellow. Then, they each mix in their own secret color. Alice adds red, Bob adds blue. Now, they send their new mixed colors, orange and green, to each other. Anyone can see the orange and green cans, but that's fine, because for the final step, they each mix their original secret color into the can they just got. And boom! They both end up with the exact same final color, this brown, without ever having sent that final secret color across the wire. That is the magic of public key cryptography. It's just brilliant.
All right, on to our next tool. Because security isn't just about secrecy, it's also about integrity. How do you know that the message you just received is the exact message that was sent? That nothing was added or taken away or just changed a little bit? That's where hashing comes in.
A hash function is kind of like a wood chipper for data. You can feed anything into it. A single word, a picture, an entire movie, doesn't matter. And it spits out this short, fixed-length string of characters. We call that a hash. And this hash is a totally unique digital fingerprint of the original data.
Now, for these hash functions to be secure, they have some really important properties. The output is always the same length, no matter how big the input was. It's also a one-way street.
It's super easy to create the hash from the data, but it's practically impossible to go backward and figure out the data from the hash. And this is the big one. It's designed to be collision-free, meaning it's virtually impossible for two different inputs to ever create the same digital fingerprint.
And this is why it's so powerful for checking data integrity. Check this out. If a sender calculates the hash of their message and sends both the message and the hash, the person who receives it can do the same thing, run the message they got through the same hash function. If their hash matches the one the sender sent, they know with almost perfect certainty that the message wasn't touched. Even changing one single letter, like swapping Alex for Jeremy here, creates a completely different hash. There's no hiding.
We can make this even more powerful by adding a secret key into the mix. This is called an HMAC, or a Keyed Hash Message Authentication Code, and it is an absolute workhorse of internet security. By throwing a shared secret key into the hash calculation, you can verify not only that the data is the same, but you can also be sure it came from the only other person who knows that secret key. And that's huge, because it gives you both data integrity and authentication all in one elegant package. Okay, so we've talked about encryption for secrecy and hashing for integrity. These might feel like pretty abstract ideas, but you're using them dozens, maybe hundreds of times a day without even knowing it. Let's look at a few places you see this stuff in the wild.
Have you ever wondered how a website can check if your password is correct without actually storing your password? Well, here's the secret. They don't. When you create an account, they run your password through a hash function, and they store the hash, not the password itself. So when you log in again, they just hash the password you just typed and compare that new hash to the one they have on file. If they match, you're in. And what's great about this is that even if a hacker steals the company's entire database, they don't get your actual password.
But wait, what if two people use the same password, like password 123? Then they'd have the same hash, right? That makes it a little easier for attackers. To fix this, we use a technique called salting. Before hashing the password, the system adds a unique random string, the salt, to it. So now, even if you and I both have the password 123, because our salts are different, our stored hashes will be completely different. It's a really simple idea, but it's a vital security upgrade.
Okay, now let's zoom out and talk about trust on a bigger scale. How does your browser know that the website you're visiting is really your bank and not some scammer's imposter site? The answer is a digital certificate, which is basically an electronic passport. It's a file that uses cryptography to prove the identity of a website.
And the core of this whole system is the digital signature, which cleverly combines everything we've been talking about. So to sign a message, the sender first creates a hash of the data. Then, and this is the crucial part, they use their own private key to encrypt that hash. This encrypted hash, that is the digital signature.
So how does the receiver verify it? It's a brilliant two-step check. First, they use the sender's public key to decrypt the signature. That reveals the original hash that the sender made. Second, they calculate their own hash from the message they just received. Now, if those two hashes match perfectly, it's a cryptographic slam dunk. It proves two critical things. One, the message is authentic. Only the sender's public key could unlock that signature, which means it had to have been locked by their private key. And two, the message has integrity. Because the hashes match, we know the message wasn't changed by a single bit while it was traveling. This one process delivers authentication, integrity, and non-repudiation, all at once. It's amazing.
So as we wrap up here, it's pretty clear that these tools aren't just for spies and secret agents anymore. They are the invisible, essential architecture of our modern digital lives.
I mean, everything from secure online banking and private messaging to just knowing that a software update is legit relies on this foundation. Encryption gives us the secrecy, hashing gives us the integrity, and digital signatures give us the proof. And together, they create the trust that makes our digital world actually work.
But, you know, this game of cat and mouse never really ends. The techniques we've talked about today are the state of the art right now. But adversaries are always getting smarter and computers are always getting faster. So that brings us to a final, really critical question. What comes next? What new cryptographic tools will we need to invent to protect ourselves in a world with quantum computing and powerful AI? The need for digital trust is only going to grow, and so will the incredible science of keeping secrets.